1.5.2. Graphing functions using reflections about the axis. Another transformation that can be applied to a function is a reflection over the x or y axis. A vertical reflection reflects a graph vertically across the x-axis, while a horizontal reflection reflects a graph horizontally across the y-axis. The reflections are shown in Figure 12. Figure 12. X, y. F of x is the original function. F of negative x is the horizontal reflection. Negative f of x is the vertical reflection. Figure 12. Vertical and horizontal reflections of a function. Notice that the vertical reflection produces a new graph that is a mirror image of the base or original graph about the x-axis. The horizontal reflection produces a new graph that is a mirror image of the base or original graph about the y-axis. A. Reflections. Given a function f of x, a new function g of x equals negative f of x is a vertical reflection of the function f of x, sometimes called a reflection about, or over, or through, the x-axis. Given a function f of x, a new function g of x equals f of negative x is a horizontal reflection of the function f of x, sometimes called a reflection about the y-axis. How to? Given a function, reflect the graph both vertically and horizontally. 1. Multiply all outputs by -1 for a vertical reflection. The new graph is a reflection of the original graph about the x-axis. 2. Multiply all inputs by -1 for a horizontal reflection. The new graph is a reflection of the original graph about the y-axis. Example 9. Reflecting a graph horizontally and vertically. Reflect the graph of s of t equals square root of t. A. Vertically and b. Horizontally. Solution. A. Reflecting the graph vertically means that each output value will be reflected over the horizontal t-axis as shown in Figure 13. Figure 13. T. S of t. Vertically reflected to t. V of t. Figure 13. Vertical reflection of the square root function. Because each output value is the opposite of the original output value, we can write v of t equals negative s of t, or v of t equals negative square root of t. Notice that this is an outside change, or vertical shift, that affects the output s of t values, so the negative sign belongs outside of the function. B. Reflecting horizontally means that each input value will be reflected over the vertical axis as shown in Figure 14. Figure 14. T. S of t. Horizontally reflected to t. H of t. Figure 14. Horizontal reflection of the square root function. Because each input value is the opposite of the original input value, we can write h of t equals s of negative t, or h of t equals square root of negative t. Notice that this is an inside change or horizontal change that affects the input values, so the negative sign is on the inside of the function. Note that these transformations can affect the domain and range of the functions. While the original square root function has domain, open square bracket, 0, infinity, closed parenthesis, and range, open square bracket, 0, infinity, closed parenthesis. The vertical reflection gives the v of t function the range, open parenthesis, negative infinity, 0, closed square bracket, and the horizontal reflection gives the h of t function the domain, open parenthesis, negative infinity, 0, closed square bracket. Try it. Number 5. Reflect the graph of f of x equals the absolute value of x minus 1. A. Vertically and b. Horizontally. Example 10. Reflecting a tabular function horizontally and vertically. A function f of x is given as Table 6. Create a table for the functions below. A. G of x equals negative f of x. B. H of x equals f of negative x. Table 6. X. f of x. For x equals 2, f of x is 1. For x equals 4, f of x is 3. For x equals 6, f of x is 7. For x equals 8, f of x is 11. Solution. A. For g of x, the negative sign outside the function indicates a vertical reflection, so the x values stay the same, and each output value will be the opposite of the original output value. See Table 7. Table 7. X. F of x. For x equals 2, f of x is negative 1. For x equals 4, f of x is negative 3. For x equals 6, f of x is negative 7. For x equals 8, f of x is negative 11. B. For h of x, the negative sign inside the function indicates a horizontal reflection, so each input value will be the opposite of the original input value, and the h of x values stay the same as the f of x values. See Table 8. Table 8. X. F of x. For x equals negative 2, f of x is 1. For x equals negative 4, f of x is 3. For x equals negative 6, f of x is 7. For x equals negative 8, f of x is 11. Try it number 6. A function f of x is given as Table 9. Create a table for the functions below. Table 9. X. F of x. For x equals negative 2, f of x is 5. For x equals 0, f of x is 10. For x equals 2, f of x is 15. For x equals 4, f of x is 20. A. G of x equals negative f of x. B. H of x equals f of negative x. Example 11. Applying a learning model equation. A common model for learning has an equation similar to k of t equals negative 2 to the power of negative t plus 1, where k is the percentage of mastery that can be achieved after t practice sessions. This is a transformation of the function f of t equals 2 to the power of t shown in Figure 15. Sketch a graph of k of t. Figure 15. T, f of t. Solution. This equation combines three transformations into one equation. 1. A horizontal reflection. F of negative t equals 2 to the power of negative t. 2. A vertical reflection. Negative f of negative t equals negative 2 to the power of negative t. 3. A vertical shift. Negative f of negative t plus 1 equals negative 2 to the power of negative t plus 1. We can sketch a graph by applying these transformations one at a time to the original function. Let us follow 2 points through each of the 3 transformations. We will choose the points 0, 1, and 1, 2. 1. First, we apply a horizontal reflection. 0, 1, negative 1, 2. 2. Then, we apply a vertical reflection. 0, negative 1, 1, negative 2. 3. Finally, we apply a vertical shift. 0, 0, 1, 1. This means that the original points, 0, 1, and 1, 2, become 0, 0, and 1, 1, after we apply the transformations. In Figure 16, the first graph results from a horizontal reflection. The second results from a vertical reflection. The third results from a vertical shift up 1 unit. Figure 16, A. T, f of t. Horizontal reflection. Figure 16, B. T, f of t. Vertical reflection. Figure 16, C. T, k of t. Vertical shift up 1 unit. B. Analysis. As a model for learning, this function would be limited to a domain of t is greater than or equal to 0, with corresponding range, open square bracket, 0, 1, closed parenthesis. Try it number 7. Given the toolkit function f of x equals x squared, graph g of x equals negative f of x, and h of x equals f of negative x. Take note of any surprising behavior for these functions. 1.5.3. Determining even and odd functions. Some functions exhibit symmetry so that reflections result in the original graph. For example, horizontally reflecting the toolkit functions f of x equals x squared, or f of x equals the absolute value of x, will result in the original graph. We say that these types of graphs are symmetric about the y-axis. Functions whose graphs are symmetric about the y-axis are called even functions. If the graphs of f of x equals x cubed, or f of x equals 1 over x, were reflected over both axes, the result would be the original graph, as shown in Figure 17. Figure 17. A. The cubic toolkit function. F of x equals x cubed. B. Horizontal reflection of the cubic toolkit function. F of x equals f of negative x. C. Horizontal and vertical reflections reproduce the original cubic function. F of x equals negative f of negative x. We say that these graphs are symmetric about the origin. A function with a graph that is symmetric about the origin is called an odd function. Note: a function can be neither even nor odd if it does not exhibit either symmetry. For example, f of x equals 2 to the power of x is neither even nor odd. Also, the only function that is both even and odd is the constant function f of x equals 0. A. Even and odd functions. A function is called an even function if for every input x, f of x equals f of negative x. The graph of an even function is symmetric about the y-axis. A function is called an odd function if for every input x, f of x equals negative f of negative x. The graph of an odd function is symmetric about the origin. How to? Given the formula for a function, determine if the function is even, odd, or neither. 1. Determine whether the function satisfies f of x equals f of negative x. If it does, it is even. 2. Determine whether the function satisfies f of x equals negative f of negative x. If it does, it is odd. 3. If the function does not satisfy either rule, it is neither even nor odd. Example 12. Determining whether a function is even, odd, or neither. Is the function f of x equals x cubed plus 2x even, odd, or neither? Solution. Without looking at a graph, we can determine whether the function is even or odd by finding formulas for the reflections, and determining if they return us to the original function. Let's begin with the rule for even functions. F of negative x equals, open parenthesis, negative x, closed parenthesis, all cubed, plus 2, times, open parenthesis, negative x, closed parenthesis, equals, negative x cubed, minus 2x. This does not return us to the original function, so this function is not even. We can now test the rule for odd functions. Negative f of negative x equals, negative, open parenthesis, negative x cubed, minus 2x, closed parenthesis, equals, x cubed, plus 2x. Because, minus f of negative x equals, f of x, this is an odd function. B. Analysis. Consider the graph of f in Figure 18. Figure 18. X, f of x, f. 1, 3. Negative 1, negative 3. Notice that the graph is symmetric about the origin. For every point, x, y, on the graph, the corresponding point, negative x, negative y, is also on the graph. For example, 1, 3, is on the graph of f, and the corresponding point, -1, -3, is also on the graph. Try at number 8. Is the function f of s equals s to the fourth power plus 3s squared plus 7, even, odd, or neither?